Continuing with section 5.1, we had last thing we showed was this note that if x1 and x2 are two eigenvectors of corresponding to the same eigenvalue lambda, then their sum x1 plus x2 is also an eigenvector corresponding to lambda. So the y was shown. You can go to the page and see why. Okay, so now the next thing is what are eigenspaces? If A is an n by n matrix with an eigenvalue lambda, then the set of all the eigenvectors of lambda together with the zero vector is a subspace of Rn. This subspace is called the eigenspace of lambda. Now in the last video we showed that if x is an eigenvector, x is an eigenvector, then Cx will also be an eigenvector. We showed it here, and then we showed that if x1 and x2 are eigenvectors, then x1 plus x2 is also an eigenvector. And if we also say can show that the zero is also in the set, so these two put everything together, and then we include the zero vector as well, then that becomes a subspace of Rn. Okay, the eigenvectors of A corresponding to lambda are the non-zero solutions of this equation, A minus lambda I times x is equal to 0. Now, and up until now, we had not learned a new technique to find the eigenvectors. We were using our row reduction to find the eigenvectors, but now we will learn a new technique in the next section. But this equation will come in handy over there. Okay, so for now, the eigenvectors of A corresponding to lambda are the non-zero solutions of this equation. What does that mean? It means these are the solutions are the basically they make up the null space. So eigenspace of lambda is the null space of A minus lambda I. So how do we get this equation? Well, we started with Ax equals to lambda x, which can lead us to Ax minus lambda x is equal to 0. Now all are vectors, so on the right hand side we have vector. So now what? I can factor out the x, so I get A minus lambda. I'm going to factor out the x here. So this is not correct because this is saying subtract a number from a matrix. We cannot do that. That is not permissible. So, but in order to create a matrix here of the same order as A, we multiply the lambda by I. I is the n by n matrix, which is the size of the A matrix. So we have this right now. That is the equation we need to solve. So let us look at an example here. Let A be this 4 by 4 matrix. And given that 1 and 2 are eigenvalues of A, find a basis for the corresponding eigenspaces. So how do we start it? Well, if you recall, how do we solve this one? We have a matrix times a vector which we want to find out equal to the zero vector. So we will find matrix first for the lambda, given lambda, and then we will put it in a matrix and augment the zero vector with it, and then apply the row operations. So down here I have done some work for you so that it doesn't take too much time. So we say let x is equal to x1, x2, x. By the way, here lambda is equal to 1. We are doing the example with lambda equals 1. We say let x1, x2, x3, x4 be the eigenvector of A corresponding to lambda equal to 1. Then we have that Ax is equal to lambda x, which means Ax is equal to 1 into x, which means A minus I times x is equal to 0. So what does now tell us? That we try to find A minus I. So A minus I put them together, A, and this is I. Now we try to subtract, so 1 minus 1, so I get a 0. Then the next three are 0, 0, 0. The next line, so we have 0 here, 1 here, and then I have 1 here. So 1 minus 1, 0. So the second line is 0, 0, 5, negative 10, because 5 minus 0 is 0, negative 10 minus 0 is 5 minus 0 is 5, and negative 10 minus 0 is negative 10. Then the third row, the first entry, 1 minus 0 is 1. Then we have 0 minus 0 is 0. And then we have third entry is 2 here and 1 here. So 2 minus 1 is positive 1. And then last entry, 0 minus 0 is 0. In the row 4, so 1 minus 0 is 1. 0 minus 0 is 0, 0 minus 0 is 0, 3 minus 2, 3 minus 1 is 2. So this is our A minus I matrix. Now I take this matrix, put it in here, and augment with 0, 0, 0. So since the first row is all zeros, so we have to swap. I swapped it with the last row. So row 1 swapped with row 4. And also at the same time I noticed that these numbers, so I can divide by 5 to simplify things. When I divide by 5, the second row becomes 0, 0, 1, negative 2, 0. First row is now the fourth row, 1, 0, 0, 2, 0. And the fourth row is the first row, which because we swapped them. So just do a couple of more row operations. So you get multiply the R1 by negative 1 and add in the R3 to make this 0. When we do that, then negative 1 plus 1 is 0, 0 minus negative 0 plus 0 is 0, then 0, negative 0 plus 1 is 1. And then we have negative 2 plus 0. So we end up getting a negative 2 in the third place. And what is going to be here? So 1 is here, 1 minus 1, third place is giving you 0. No, it's giving you 1, sorry. What did we multiply, because it's 0 minus 1. So it's giving you negative 0 plus 1 is 1. Now we can see that this is a pivot and this is the pivot. So get rid of this 1 here. So multiply the second row by negative 1 and add in the third row. Gives us 2 rows of zeros. which is showing us, because these are the pivot rows, so these are not free, these are what we call the basic variables. So what are the free variables? We have x2, x1 and x4, because we don't have pivots in there, and x4 are free variables. So now we can keep them as x2 and x4, or we can call them s and t. We'll see. Just let's first write our equations. So our equations are, first equation gives me x1 plus 2x, sorry, x2 plus x1 plus x4, 2x4 is equal to 0. And then the second is x3 plus minus 2x4 is equal to 0. So this gives me x1 is equal to 2x4, x3 is equal to, when x1 is negative 2x4, so x1 is negative 2x4 from here, and from here x3 is equal to 2x4. So what is x2? Well, x2 is just x2. And if you want here, I will show you how to. So x4 is x4. So if you write in terms of x2 and x4, you can go ahead, but I prefer giving them different names. So x2 is equal to s and x4 equals t. Then x1 is equal to negative 2t, x2 equals s, x3 equals 2t, and x4 equals t. Now x is negative 2t, s, 2t, and t. So this can now be written as, split the s and the t. We have 0, 1, 0, 0, s outside. And then for the second one, plus t outside, negative 2, 0, 2, 1. So now we say that these are the, so because remember we were looking at what the basis of eigenspace of lambda equal to 2. So the eigenspace for lambda is equal to 2. What is the basis? It is the set which contains these two vectors. You may also write it like this, that the eigenspace over lambda is span of these two vectors. Okay, so I did this example for you guys. So now I want you to try to find the eigenspace for lambda is equal to 2. This was for lambda is equal to 1, sorry. So this was lambda is equal to 1, and now we have to do it for lambda is equal to 2. So I will let you guys try and then come back and see the next video.